Thank you for watching this video abstract. Let's start with a brief history on phi gamma modules. So, fixed K complete discretization field over P with perfect residue field small k, still no GK absolute Galois group. And so the idea is to classify all the GK representations. The clever idea is to put in the middle KP infinity intermediate field. So by definition, we're adding all the p power roots of unity to K. When K is unramified, this is the so-called cyclotomic extension of K. So we call this case a cyclotomic case. And this part of GKP infinity representations, it could be classified by certain phi modules. This is from the genius field of norm theory by Fontaine and Beijing. And so this part of phi module action, phi module information and this gamma action put together, you got a semi-linear data called phi gamma modules. The big theorem of Fontaine tells you that a tau phi gamma modules classify all the ZP representations. Okay. And then a natural question is, can we recover some interesting invariants using this in priori simpler semi-linear data? The answer is positive for Galois cohomology. So the first result is given by Herr in his thesis. He constructed a nowadays called F complex consisting of 3 terms and gives you back this Galois cohomology of the associative representation in terms of phi gamma modules. And let me remark there are also variant versions refined phi gamma modules. So there are versions over the overconvergent rings given by Shepard and Comet, over the robot ring by Luming. For all these variants, so the corresponding results on analog of L complexes given by Comet and Rochen-Liu. How about the phyton modules, our topic today? So let me go back to the diagram again. The idea is to replace this cyclotomic extension KP infinity by a Kummer extension called K infinity. So by definition, we add all the p power of the rows of a fixed uniformizer of K. I put it there. The problem is now it's no longer a Galois extension. And this part of GK infinity representations is still fine for the same reason classified by phi modules again. So some choices for this part. Choice 1, fix the Galois closure. You get this L over K denote the group G hat. And then Tong Liu tells you that this piece of phi modules and a G hat action at extra conditions gives you the so-called phi G hat modules. It could classify all the semi-stable representations. This could be seen as a generalization of the Peking modules for Chris-Hani representations, roughly speaking. This also tells you why we're interested in this phi G hat and later phyton modules, because this Peking modules play a central role in integral p-adic Harsh theory nowadays. Okay, so second choice, capital tells us that we could pick a clever choice of the topology generator for this L over KP infinity. And then this phi module and a tau action. So be careful, this tau action is not stable over the phi module. It's get out of this coefficient ring for a bigger ring. And extra group theoretic requirements to make sure that you could glue back this Galois representation. And the big theorem again tells you could classify the p representation of JK. How about the L complex? So for phi G hat modules, sometimes this is analog of L complex is given by Tyvek-Seebeck-Ho's complex. 4 terms, 3 operators, phi gamma and tau. And for phyton modules, this is the main theorem of our article. So we construct a complex with 3 terms, so analog of L complex using phyton modules. So you see this is already some new phenomenon here. So this DL0 is a very bizarre module. Before we are only having phi modules, but this DL0 is not phi module. Actually, this DL0, so we can see it motivates our construction of the complex. So in the first proof, let's say, look at the proposition here, this precise computation of H1 forced this DL0 to appear right there. Second remark is that, so the first proof give you, by standard techniques, delta functor irreversibility, but there are also other new phenomena. For example, just to show very obvious thing for the cyclotomic case, which is the functor from the representation to the homology of the complex is a delta functor. In our case, this is not very easy. Actually, we have to use almost purity for perfectoid fields. So as application of this, so we put in the middle some results on the vanishing of certain Galois groups. We think it's interesting for its own reason. Okay, and finally, the final remark is that, so our complex actually refined the complex of Tyvek-Seebeck-Ho in the sense that we can construct a precise morphism and show that it indeed is a quasi-isomorphism. So actually, this idea could be generalized more conceptually to cover simultaneously the overconvergent and rigid overconvergent cases in following work with Hui Gao. So thank you for your attention.